Hey guys, welcome back to the Introduction to Elixir tutorial series. This will be part 9 of this series. Today we're going to build upon what we've learned about server processes, and we're going to start to look at some of the concepts that exist inside of the OTP platform, or the Open Telecom platform. Mainly we're going to implement what's called a generic server process. The generic server process is actually given to us by OTP in the form of a library called GenServer. Now OTP has a bit of a misleading name, Open Telecom Platform. It's not really about telecoms. It's actually rather about providing patterns and abstractions for tasks. In the last tutorial, we implemented a calculator application that ran in its own process. And the idea here is that the process itself was able to maintain its own state. So we were able to spawn a separate process and then run an infinite loop inside of the process via the loop function here. And then this infinite loop would then maintain our process state by reacting to the different messages that we were sending to the process. And then of course this process was able to send back responses to the caller. Now, no matter what kind of server process you create, you're always going to need to do these tasks. And so it's worth moving this code into a single place and then creating an abstract implementation of it so that we can reuse the code in our own concrete implementations. The idea here is that our generic implementation will be able to perform various tasks which are common to server processes, leaving the specific decisions to the actual concrete implementation. For instance, the generic code will spawn a process, but the concrete implementation must determine the initial state of the process. The generic code will also receive a message and then optionally send the response, but the concrete implementation must decide how that message is handled and what the response is. In other words, the generic code drives the entire process, and the specific implementation must fill in the missing pieces. And so we need a sort of plug-in mechanism that lets the generic code call into the concrete implementation when a specific decision needs to be made. Our primary way of doing this is by using modules. Remember that a module name is an atom, and you can store that atom in a variable and then use the variable later to invoke functions on the module. So for instance, I can take the IO module, put it in a variable called IO module, and then I can call to any of the functions inside of the IO module dynamically by calling to the variable. And so this feature can allow us to provide a callback hook from our generic code. And so we can make the generic code accept a plugin module as an argument, and that module is called a callback module. And then we maintain the module atom as part of the process state, and then invoke the callback module functions when needed. Alright, so let's go ahead and start to write our generic server. So first I'm going to define a module called generic server. And this will contain all of our generic server logic. Now, inside of our generic server, we want to be able to take in a module atom, which will be the actual concrete implementation, or the callback module. And then we can use this to then spawn a process. So we'll create a start function here that takes in the module name. And then we'll go ahead and we can say spawn. And inside of spawn, what we'll do is we'll call to a function inside of our module called Init, which will give us our initial state. And then we'll call to a loop function, which we'll create here in a moment. And we'll pass in the module atom and then the initialized state. So like we saw with our calculator server, we're still going to be using a loop that will be able to then read the different messages and stuff. But we are also going to be adding this init function, which will make it very easy for us to define the initial state for our concrete module. Now here's what our loop function is going to look like. So we pass in the module and then the current state. And then we have a receive block where we have a tuple that is looking for a pattern of request and caller, where request is the data that identifies the request and is meaningful to the specific implementation. And then the caller is the process ID of the process that is calling to this server. We then want to invoke a callback function, which we're going to call handle call, and we'll pass in the request and our current state. This call will give us back a response, and then it will give us back our new state. And then at the bottom, we'll be able to call send so that we can send information back to the process. So we send back to the caller a response with response in it, and then we can continue looping with the module name and then the new state inside of it. Now we need to provide a function to issue requests to the server process, and we'll call this function call. So call will take in the server process ID and then the request. And then with this information, we can call send with the server process ID, and then we can pass in a tuple of our request, and then we can call to self to get our process ID. With call, we're also going to want to wait for a response, and so we can go ahead and add another receive block here, which will just look for a response and then return that response like this. Now, this is all it really takes to create a very simple implementation of Gen Server. If we wanted to, we could go ahead and use this implementation to redefine our calculator, or we could use it to take our task list and convert it into a server process. Now, in our current code, we use this call function to handle synchronous requests from other processes. For asynchronous requests, we can use a term called cast. And this is the naming convention that you'll find in Gen Server itself. So let's go ahead and create this cast function. Because we're going to be implementing a second request type, we need to change the format of the messages that are being passed between the client process and the server. And this will allow us to determine the request type in the server process and then handle the different types of requests in different ways. Fortunately, this is actually pretty simple, so all we really need to do is use an atom to let the server know that we're using the call function, and so we can just expand the send call here and have it start with an atom call. And then inside of our loop, we also want to add the call atom to the front of the tuple that we're receiving from the client. And this then connects these two functions together. So now when we call to the call function, it will create a message of this format, and our receive block will then know how to handle this format. Now we can go ahead and implement a function to handle cast requests. And so the idea here is that when the message arrives, the specific implementation will handle it and then return a new state. However, no response will be sent back to the caller, and so the callback function must return only the new state. And so our function here just takes in the server process ID and then the request, and then it just calls send on the server process ID with a tuple of cast and request inside of it. Now we can go ahead and add the cast case to our receive block. So we're looking for a tuple of cast and request, and then we're going to define our new state by calling module handle cast with request and then the current state. And then we're going to take our new state and pass it into loop. So you can see that our call function has this extra step where it's sending the data back to the process that's calling to this server, whereas cast does not have this extra step. Now let's go ahead and use this generic server with our task list code. And I'm just going to leave the task list code alone. And we're going to implement a module on top of the task list called task server. And this module will then allow us to interface with the server process. Define module task server, and then we can define the various different callback functions that we are going to need to interface with the server. So first we want to define the client side code. So we need to define a start function which will start the process. And remember, the start function just is going to call to our generic server start implementation, and we're going to just pass in the task server atom, which is just the module name. And so this will allow us to bind the process to the module name so that we have our specific functionality. Now remember, when we call to this start function, we also want to call to a module init function, and so we need to create this init callback function inside of our task server module. All the init function does is define the initial state for our process. So all we really need to do is call to our task list code and then call the new function, which will then set up the state for a task list. If you remember, it just takes and creates our structure, and it also allows us to pass in entries if we want to. But since we're calling new with no arguments, we'll just create an empty task list struct. Now let's go ahead and create a way that we can actually add a task to our generic server process. So we'll create a function called add task. We'll pass in the server process ID and then the new entry that we want to add. And in here, we're going to call to our cast function. And remember, the cast function allows us to call asynchronously to the process. So the process doesn't have to send back an actual response for getting this particular call. And so we just pass in the server process ID, a tuple of add task, and then the new entry. Then on the server side, we need to define the callback function, the handle cast callback function that is, and we need to basically add in the details to tell it how we want it to handle the tuple of add task and new entry. Our call to cast will look like this. So we have the cast itself followed by the request, which will be that actual tuple. And then we want to call module handle cast, which takes in the request, which is the tuple that we just passed in, and then the current state of our process. And so inside of this function, we have access to the actual request, and then we have access to our state. And so we can go ahead and call task list add task to the state of the process, and then we want to put in that new entry. Now let's go ahead and implement a getTasks function, which will allow us to read a task from our server's state by its date. So we pass in the server process ID and then the date, and then we're going to call generic server.call because we want to actually have a response. And we'll pass in the server process ID and then a tuple of get tasks followed by the date. And so when we call to the call function, this send call will actually look like this. So it will have the process ID, which we're sending into it, and then it will have the call here, and we'll have our call atom followed by another tuple inside, which is the actual message that we're passing in that has get tasks and the date inside of it. And then afterwards, we'll have a call to self. And so in this case, our request is going to look like this. And so we need a way to handle it inside of our loop function up here. So if we take a look up here, we have the request, which is this. So we have call, request, and then the caller, which is self. And then we need to pass back the response and the new state. So we'll call module handle call, which we need to implement. And handle call takes in the request and then the current state. And then we send back to the caller a response with our response inside of it, and then we continue our loop. So of course now we need to implement that handle call callback. And remember, the request looks like this, so we pass that in as the first argument, and then we pass in the process state, which is just our task list. Now our return will be a tuple. We'll call to task list get tasks, put in our task list and then the date, which will give us back a specific entry inside of our task list based on the date. And then we also want to pass back the entire task list. So remember, the tuple has the response first, which is the actual result of our function call, followed by the new state, which is just our task list. Because getting an entry from the task list isn't going to change the task list at all. So we just pass that unchanged state back into our process. So now we can go ahead and use our task server. Let's get the process ID, and for this we just need to call task server.start. Now let's go ahead and add an entry to our task server using the add task function. So I've created an entry up here with a date and a title. And then I can go ahead and just take the process ID, pipe it into our task server.addTask, and then put in the entry. And you can see here that we actually get back a tuple of cast add task followed by the entry that we're putting inside of the task server. Now if we want to go and recall the state of the actual entry that we just put in, we can call PID, pipe it into our task server.getTasks, and then pass in our entry.date. And you can see here that we get back a list of all of the entries with that specific date. And because we only have the one entry inside of our state, we only get back the one entry map. I'm sure you guys can see how this generic server or gen server pattern can be really useful. And so it makes sense that gen server is provided as a tool by OTP so that we don't actually have to rewrite the pattern every single time we want to implement a server process. Let's go ahead and look at how we can register processes. So in the beam, a process is identified with a corresponding process ID, and to make the process send messages to another process, you have to bring the process ID of that process to the other process. And so in a sense, the process ID sort of resembles a reference or a pointer to a process. Now, of course, when you're dealing with hundreds or thousands of different processes, it can be a pain to actually pass those process IDs around all of your code. We have the ability to register a process ID with an atom. I've gone ahead and I've called process.register on the PID that we have for our task server, and then I've put in the atom task server. As you can see here, I can just call to task server as the atom instead of the process ID and pipe that into our task server.getTasks function, and we still get back the entry that we put into the process's state. Now, there are a few rules for registering a process like this. The name of the process can only be an atom, and a single process can only have one name. So you can't have multiple atoms associated with a single process. And of course, two processes can't have the same name. We can't go ahead and register another task server with this task server atom. Now, we've already learned a great deal about how processes work, and to take full advantage of the beam's concurrency, it's important to understand some of the internals of these processes. We've already mentioned in the last video that although processes may run in parallel, a single process is always sequential. It will either run some code or it will wait for a message. If many processes send messages to a single process, that single process can significantly affect the overall throughput of the application. To show you guys an example of this, I've created a module here called server, and our server module is going to implement our generic server pattern. So we have a start function, and we're going to register this process with an atom called server. So we can call generic server start with the module inside of it, and then we can go ahead and register this process, calling process.register, and then passing in the atom that we want to register it with. Then of course we need to have an init function to initialize this state, but because I want this process to be stateless, it really doesn't matter what we put in here, so I've just put in an empty list. Then we want to define a call server function, which will just take in a message. And notice because we have the atom here, we don't actually have to pass in the process ID because we can just reference it or hard code it directly into here. We go ahead and we call generic server.call. We're calling it on the server atom, and then our request is going to look like this. So we pass in an atom called request, and then we're going to have a string here which will say message, followed by a string interpolation of the message that we're passing in here. Then when we handle this message, we want to make the process sleep for a second, and then we'll pass back a tuple of message and then the changed state, which will just continue to be an empty list. So essentially what this will do is it will just pass back a string after a second with our call inside of it. So now let's go ahead and start our server by running server.start. And of course we get back true because we're binding our process ID to that atom. So now we can go ahead and use enum each to spawn 10 different parallel processes which will call to our server process. We'll call enum each from range 1 to 10, then we'll use an anonymous function to pass that value into our spawn call, and of course spawn takes in an anonymous function itself. In this function, we want to print that we're sending in the message, which will be one of these values. Then we want to get the response, which we'll just get by calling server.callServer with X inside of it. And then we want to print out that response using IO puts. As you can see, all of the messages get sent almost instantly, but notice each of the responses comes back after a second. So even though all of our processes are running in parallel, they're all calling to this one process, and because we've put in logic to have the process sleep for a second, the process can only handle one of the messages at a given time. Now, generally a server process has a simple flow. It just receives and it handles a message one by one. So the goal here is to make the server handle the messages at least as fast as they arrive. In this example, our server optimization would just amount to removing the process sleep call. If you can't make the message handling fast enough though, you can try to split the server into multiple different processes. Now theoretically, a process's mailbox has an unlimited size, and so this is where our real problem comes. Not only would this be very slow, it also would potentially use up a ton of memory. The mailbox will just increase until it takes up all the available memory, and then it will crash the system. And so this is why you need to find a way so that you do not have a process that is bottlenecking your application. Alright guys, well I hope you enjoyed this tutorial. If you did, feel free to like and subscribe. If you have any questions or comments, feel free to leave them in the box below. And if you dislike this video, then by all means downvote it as much as you like. If you want to catch future videos in the Intro to Elixir tutorial series, then I recommend you ring that notification bell so that you get a notification when I actually post them. Alright guys, have a good night.